When people discuss interstellar travel, sending humans to other star systems, the focus usually lands on the obvious challenges. The enormous distances, the vast energy requirements, the decades, or even centuries of travel time, the problem of keeping humans alive. These are all very real, certainly. But there's another issue, one that's rarely discussed in popular accounts of space exploration, one that might be even more fundamental and difficult to overcome. Interstellar dust and debris. At the speeds required for practical interstellar travel, significant fractions of light speed, even tiny particles transform into catastrophic threats. A speck of dust, smaller than a grain of sand, something you wouldn't even notice on Earth, becomes a kinetic weapon, capable of punching straight through your spacecraft and killing everyone inside. The interstellar medium, which seems empty from our everyday perspective, turns into a minefield of deadly projectiles when you're moving at 10% or 20% of light speed. This isn't science fiction speculation or theoretical hand-waving. This is straightforward physics confirmed by our observations of space. And it represents a potentially insurmountable barrier to the kind of fast interstellar travel that would make reaching other stars feasible within a human lifetime. Let me walk you through why this problem is so severe, why it's so difficult to solve, and why it fundamentally challenges our dreams of an interstellar civilization. We should start with the basic physics of high-velocity impacts, because understanding the energies involved is crucial to grasping the severity of the problem. Kinetic energy. The energy of motion is given by the formula E equals 1/2 mv superscript 2, where m is mass and v is velocity. Notice that the energy depends on the square of the velocity. This means if you double your speed, you quadruple the kinetic energy. If you increase speed by a factor of 10, you increase the energy by a factor of 100. Now, the speed of light is about 300,000 kilometers per second. If you're traveling at 10% of light speed, a relatively modest target for interstellar travel, that would get you to the nearest star in about 40 years. You're moving at 30,000 kilometers per second. That's about 100 times faster than the fastest spacecraft we've ever built. At these velocities, the kinetic energy of even the tiniest particles becomes enormous. Let me give you some concrete numbers to make this visceral. Consider a particle with the mass of a single grain of sand, about 1 milligram or 10 kilograms. If your spacecraft hits this particle while traveling at 10% of light speed, the kinetic energy of the impact is approximately 450,000 joules. That's equivalent to the energy released by about 100 grams of TNT or a small hand grenade. A single grain of sand at 10% light speed carries the kinetic energy of an explosive. And it's not just the energy that matters. It's the power, the rate at which that energy is delivered. The impact happens in a tiny fraction of a second, depositing its energy instantly and creating enormous pressures and temperatures that can vaporize material, create shock waves, and punch holes through solid metal. Now, scale this up. If you hit a particle the size of a pebble, say 1 gram instead of 1 milligram, at 10% light speed, the impact energy is 450 million joules, equivalent to about 100 kilograms of TNT. That's a small bomb. A pebble-sized piece of rock at these speeds would obliterate anything it hit. And if you hit something the size of a golf ball, about 45 grams, the impact energy would be equivalent to roughly 10 tons of TNT, about the yield of the smallest tactical nuclear weapons. At 20% light speed, the energies would be 4 times higher. At 50% light speed, sometimes proposed for very fast missions, they'd be 25 times higher. These aren't abstract calculations. This is what would actually happen if your spacecraft, traveling at relativistic speeds, collided with interstellar debris. And here's the crucial question. How much debris is actually out there? The interstellar medium is not perfectly empty. The space between stars contains gas, mostly hydrogen, some helium, at very low densities, typically about 1 atom per cubic centimeter. That's an extraordinarily good vacuum by terrestrial standards, far better than anything we can create in labs on Earth. But it's not zero. More importantly, the interstellar medium also contains dust, small solid particles ranging from molecules up to grains the size of sand or larger. These dust grains are created by dying stars, supernova explosions, and collisions. They're spread throughout the galaxy, though their density varies. In the general interstellar medium, the space between star systems, away from dense clouds, the dust density is roughly 1 grain per cubic kilometer. That might sound incredibly sparse. A cubic kilometer is a huge volume. 1 grain per cubic kilometer seems negligible. But now consider your spacecraft traveling at 10% light speed, 30,000 kilometers per second. In 1 second, your spacecraft sweeps through a cylinder of space 30,000 kilometers long. If we assume your spacecraft has a cross-sectional area of, say, 100 square meters, a modest size, then in 1 second you sweep through a volume of about 3,000 cubic kilometers. At 1 dust grain per cubic kilometer, that's about 3,000 dust grains per second hitting your spacecraft. Over a 40-year journey to Alpha Centauri, you'd encounter roughly 4 trillion dust grain impacts. 4 trillion tiny explosions, each releasing the energy of a hand grenade or more, scattered across your spacecraft surface. Now, not all would be catastrophic. Many would hit thick parts of the structure or shielding. But many others would hit vulnerable areas. Sensors, antennae, solar panels, cooling systems, life support, hull seams. Even if only a tiny fraction caused serious damage, you're looking at potentially billions of damaging impacts over the journey. And this assumes you're traveling through relatively empty space. If you pass through a region with higher dust density, near a nebula or a star-forming region, the impact rate could be hundreds or thousands of times higher. Passing through such a region at high speed will be like flying through a sandstorm made of grenades. Moreover, we're not just talking about dust. There are also larger objects, pebbles, rocks, chunks of ice, fragments from asteroid collisions. These are much rarer, but they exist. Hitting even a single pebble-sized object could be catastrophic. Estimates suggest that on a journey to Alpha Centauri, a spacecraft might encounter several particles in the centimeter-size range, and possibly even larger. Each carries enough energy to potentially destroy the spacecraft. So we have a fundamental problem. To reach other stars in reasonable time, we need significant fractions of light speed. But at those speeds, the interstellar medium becomes a continuous barrage of high-energy impacts, any one of which could be fatal. How do we solve this? Let's examine the proposed solutions and why each is problematic. The first, most obvious solution is shielding. Build thick armor to absorb impacts. This is how we protect craft in Earth orbit from micrometeoroids. Using Whipple shields, multi-layer structures that break up and vaporize incoming particles. But here's the problem. At interstellar velocities, the required shielding becomes impractically massive. When a high-velocity particle hits a shield, it vaporizes, creating a plasma cloud and shrapnel. A good shield uses multiple layers, an outer bumper to vaporize the particle, a gap for the plasma to expand, and an inner wall to stop fragments. For this to work at 10% light speed, you need a bumper several centimeters thick, a gap of perhaps a meter, and a thick inner wall. This structure must cover the entire forward-facing area. Now calculate the mass. If your spacecraft has a forward cross-section of 100 square meters and you need shielding with a total mass of, conservatively, 100 kilograms per square meter, that's 10,000 kilograms, 10 tons, just for the forward shield. And you need shielding on other surfaces, too. This might not sound insurmountable, but remember the rocket equation. Every kilogram of shielding requires additional fuel to accelerate it, which requires more fuel to accelerate that fuel, and so on. Moreover, 10 tons might protect against dust grains. To protect against centimeter-sized rocks, you'd need shielding meters thick, escalating the mass to hundreds of tons. To protect against rarer, larger objects, the shielding becomes so massive the spacecraft is impractical to accelerate. There's a fundamental trade-off. Thicker shielding means more mass, which makes achieving high speed harder, which means longer journey times. You can't solve this with shielding alone without making the spacecraft too heavy for practical interstellar travel. The second proposed solution is active deflection. detecting incoming particles and using lasers, magnetic fields, or other means to deflect or destroy them before impact. This sounds like science fiction, but let's examine it. For active deflection to work, you need 1. To detect incoming particles at long range, extremely difficult as dust grains are tiny and reflect little light. 2. To identify which particles pose a threat among thousands per second. And 3. A deflection mechanism that works quickly and precisely. If you detect a particle 1,000 kilometers ahead at 10% light speed, you have only 1/30 th of a second to deflect it. Lasers are the most common proposal. Vaporize part of the particle to create a jet that pushes it off course. But the power requirements are daunting. You need laser power in the gigawatt range for effective deflection of dust grains at 10% light speed, comparable to a large power plant. And you need to power this continuously for decades. Where does this power come from? Nuclear reactors add mass. Fusion is speculative, and you can't deflect everything. Particles too small or approaching from blind spots will get through. Crucially, active deflection doesn't help with larger objects. They're too massive to deflect with realistic laser power on short notice. The third solution is navigation, plotting a course that avoids regions of high dust density. This has merit. We can map large-scale dust structures, but limitations are severe. Our maps are incomplete and low resolution. We can't know the dust density in a specific cubic kilometer. Even empty regions aren't truly empty. The baseline is about 1 grain per cubic kilometer. Navigation constraints limit options. Going around a dusty region might add decades to the journey. And dust distribution can change over time due to supernovae or stellar winds, making your carefully planned route hazardous mid-journey. Navigation reduces risk, but doesn't eliminate it. The fourth solution is redundancy and self-repair, designing the spacecraft to tolerate damage and fix itself. This is sensible. Any interstellar craft would need redundancy, but there are limits. If a pebble-sized rock hits, releasing bomb-level energy, that section is simply destroyed. Redundancy means backup systems elsewhere, but it doesn't prevent the loss. If impacts are frequent, thousands per second, cumulative damage over decades becomes overwhelming. You can't repair damage faster than it occurs. Plus, self-repair requires spare parts, equipment, and crew or robots, adding mass. Now, the solution most commonly proposed by serious mission concepts. Don't send humans. Send tiny, lightweight probes that can be accelerated to high speeds with minimal mass. This is the approach of projects like Breakthrough Starshot, gram-scale probes accelerated by powerful lasers to 20% light speed. A tiny probe has minimal cross-sectional area, encounters fewer particles, doesn't need life support, and is simpler and more robust. If some probes are destroyed, you send many. But notice what we've given up. We're not sending humans anymore. We're sending tiny robots that can take pictures and transmit data, but can't establish colonies, can't explore in detail. We've scaled down our ambitions from sending people to taking snapshots with disposable cameras. This might be the most we can realistically achieve, but it's a far cry from the Star Trek vision. And even these probes face serious challenges from interstellar dust. A significant fraction will be destroyed. So where does this leave us? We have a fundamental problem. Interstellar space, while sparse, is dense enough to be extremely dangerous at relativistic speeds. Shielding is too massive. Active deflection is too power-hungry. Navigation is too uncertain. Redundancy is insufficient. Miniaturization means giving up on crewed missions. Is there any solution? Are there realistic approaches that could overcome this barrier? And what does this mean for humanity's long-term future? Are we truly confined to our solar system, not by energy or distance, but by the impossibility of surviving the journey through the interstellar gauntlet? Let me explore more exotic possibilities, because conventional approaches don't seem to work. If we're serious about interstellar travel, we need to think more radically. We've established that conventional approaches have severe limitations. Now, let's consider more unconventional ideas. First, magnetic shielding. The interstellar medium contains ionized, charged particles. A powerful magnetic field around your spacecraft could deflect them, like Earth's magnetosphere deflects the solar wind. The concept, called a magnetic sail or plasma magnet, is serious. The physics: a charged particle moving through a magnetic field experiences a Lorentz force, deflecting its trajectory. But problems: 1. Not all dust is charged. Neutral particles sail right through. 2. Generating a field strong enough to deflect relativistic particles requires enormous power. Field strengths of several Tesla extending over thousands of kilometers. This requires superconducting coils, which need cryogenic cooling, adding mass and complexity. 3. Impacts could damage the coils. 4. The magnetic field creates drag, slowing you down, requiring continuous thrust. Deflecting particles also creates electromagnetic radiation, Bremsstrahlung, synchrotron, that could interfere with systems and pose a radiation hazard. Magnetic shielding helps with charged particles, but doesn't solve the problem. Neutral dust still gets through. Another exotic idea: plasma shielding. Surround your spacecraft with a cloud of plasma, ionized gas, to absorb or deflect incoming particles. This is even more speculative. Problems: 1. Continuously generating and maintaining the plasma cloud requires enormous power. 2. The plasma needs to be dense enough to stop particles, but not so dense it creates drag. 3. Maintaining the cloud's shape around a fast-moving spacecraft is extraordinarily difficult. 4. The plasma emits radiation, creating interference and hazards. 5. Impacts release energy into the plasma, which must be radiated away or it heats uncontrollably. Combining magnetic and plasma shielding adds more complexity and power requirements. Realistically, plasma shielding seems beyond current capabilities and might face insurmountable physics challenges. A radically different approach: extreme miniaturization and hardening. Make the spacecraft so small and strong that impacts don't matter. A solid block of diamond or carbon nanotubes with embedded systems. A dust grain would create a tiny crater, but the bulk survives. Problems: 1. Making complex electronics and sensors from such materials is far beyond current technology. 2. Even diamond has limits. A sufficiently energetic impact will shatter it. 3. Miniaturization has limits. You need minimum size for meaningful instruments, power, and computation. 4. If it's so small and hardened, can it do much upon arrival? Extreme hardening might push survivability, but at the cost of functionality and with possibly impossible tech requirements. Now, the most radical idea: send information, not matter. If the goal is extending human presence, send the information needed to reconstruct civilization or even humans at the destination. Send a probe with data, human genomes, digital libraries, technology plans, even mind uploads. At the destination, use local resources to build machinery and reconstruct. The advantage: information can be transmitted as signals, radio, laser, that don't suffer particle impacts. You can send redundant copies. But problems are formidable. 1. This requires autonomous robotic systems at the destination capable of mining, refining, and manufacturing complex technology from scratch, far beyond current AI and robotics. 2. If you're creating humans or mind uploads at the destination, they have no direct connection to Earth. Are they truly us extending to the stars? 3. Profound ethical questions. Is it ethical to create humans in isolation on distant worlds? 4. This isn't travel in the traditional sense. It's creating copies. The original you remains or dies. Information transmission might extend human influence, but it's not the same as interstellar travel. Stepping back, given all this, is crewed interstellar travel actually possible? The honest answer is we don't know. But the challenges are so severe it might be impossible with any technology obeying known physics. The problem isn't just engineering, it's fundamental. The interstellar medium is lethal at required velocities. Solutions have limitations that might be insurmountable. Think about the energy budget. Accelerating a crewed spacecraft to 10% light speed requires enormous energy. Adding shielding and deflection systems adds mass, requiring even more energy. Powering deflection during the journey requires a continuous generation, probably nuclear, adding more mass. The mass spirals upward. Energy requirements become astronomical, and the mission becomes impractical. And even if we solve energy and mass, we face the probabilistic threat of a catastrophic impact with a larger particle. Even if we handle 99.9% of dust, the 0.1% that gets through over trillions of impacts could be devastating. We can't predict or prevent collisions with rare, larger objects, a cosmic deer that's a pebble moving at 10% light speed relative to you, releasing tons of TNT energy. Faster speeds make the problem worse, not better. Higher speeds mean higher impact energies, requiring thicker shielding, more mass, making high speeds harder to achieve. Above certain velocities, maybe 20 to 30% light speed, impact energies become so extreme no conceivable shielding could protect. There might be a sweet spot, speed, fast enough for reasonable time, but not so fast impacts are unsurvivable. But that might be at 1 to 5% light speed, making journeys take centuries or millennia. At those time scales, you need generation ships with their own severe problems. Here's a sobering conclusion. Crude interstellar travel might be one of those things that sounds plausible, doesn't violate physics, but is practically impossible due to engineering constraints and environmental hazards. Like traveling to Earth's core, no law prevents it, but pressure and temperature make it completely impractical. Similarly, we might never send people between stars, not because it violates relativity, but because the interstellar medium is too hazardous and engineering solutions are too massive, power-hungry, or unreliable. Objection. What about future technologies' breakthroughs? The dust problem isn't about current tech. It's about physics and arithmetic. The kinetic energy equation is fixed. The interstellar density is fixed. Better materials, power sources, shielding might help, but they don't eliminate the fundamental challenge. You're moving a fragile craft with delicate humans through a hostile environment at relativistic speeds. Perhaps some exotic physics, faster than light travel, could bypass the problem, but that's speculation. With known physics, the problem appears formidable, perhaps insurmountable for crude missions. This might even explain part of the Fermi paradox. If interstellar travel is this difficult, civilizations might arise but remain confined to their home systems, unable to spread or colonize. We might live in a galaxy full of isolated civilizations, each trapped by the same barrier: the impossibility of shielding against interstellar dust at relativistic speeds. A lonely picture, intelligence marooned on isolated worlds, able to observe but not explore. But before ending on pessimism, let's explore one more class of possibilities, changing our definition of crew and human. Maybe the solution isn't better spacecraft, but better travelers. What if we modify ourselves biologically, cybernetically, or informationally to survive conditions that would kill baseline humans? Biological modification, genetic engineering, could address other challenges: radiation resistance, extended lifespan, reduced metabolic needs, hibernation. These help at the margins, lighter life support, smaller cross-section, but don't solve the dust problem. No amount of genetic modification makes flesh resistant to explosive impacts. Cybernetic enhancement, replacing biological parts with robust mechanical ones, could increase resilience. Replace organs, limbs, enhance the brain with interfaces. A cyborg might survive radiation, and limited impact damage of components are hardened and redundant. But limits remain. Cybernetic systems are still matter vulnerable to kinetic energy. And profound questions arise about identity. At what point is it no longer the same person, no longer human? Complete consciousness transfer, mind uploading, into digital hardware. A digital mind could be radiation hardened, stored redundantly, backed up. It doesn't need biological life support, allowing lighter craft. It could tolerate longer journeys by slowing subjective time, but it still runs on physical hardware vulnerable to impacts. You can make it compact and redundant, but sufficiently energetic impacts will destroy processors, corrupt memory. Moreover, philosophical questions. Is the digital copy you? And what does it do upon arrival? Without physical infrastructure to build bodies or interact with the world, its capabilities are limited unless you also send manufacturing systems, which face the dust problem. The most extreme, abandoning physical form entirely, existing as information patterns transmitted as electromagnetic signals. Information travels at light speed, experiences no dust impacts. At the destination, it's used to instantiate a copy. Advantages: fast, no acceleration or impact problems for the transmission itself, can send many copies. But problems: requires physical infrastructure, receivers, computers, already at the destination, which must have been sent physically, facing the dust problem. Bandwidth for human consciousness is enormous, petabytes. Transmission suffers degradation, noise, attenuation. And philosophically, this isn't travel, it's creating a copy. The original you remains. These scenarios raise unavoidable questions about identity and continuity. At what point does the being at the destination cease to be you or human? We might be able to send something, but whether it's recognizably human, whether it has continuity with the senders, whether it fulfills the dream of human interstellar exploration, these are open. Why are we focused on interstellar travel? Motivations often conflated. 1. Scientific exploration doesn't require humans, robotic probes, or telescopes suffice. 2. Species survival could be accomplished within our solar system, Mars, space habitats. 3. Expansion/colonization. Resource exhaustion is millennia away, not clearly necessary. 4. Transcendence/destiny. Philosophical. Maybe digital existence or other means represent a different transcendence. Each motivation might have different solutions. Interstellar travel might be impossible for biological humans, but our other goals might be achievable through different means. One final possibility: maybe we're thinking wrong. The solution isn't going faster or protecting better, but going slower. Accept very slow travel where dust impacts are survivable, say 0.1% light speed, 300 kilometers per second. A milligram dust grain at this speed carries 45 joules, a thrown baseball, not a grenade. Manageable with reasonable shielding. The downside: journey time to Alpha Centauri for 1,000 years. Longer than recorded history. But 4,000 years might be acceptable if you're not in a hurry, if you solve generation ship problems. Closed ecosystems, social cohesion across hundreds of generations, technical failures, social breakdowns. These are severe but different challenges of engineering, ecology, sociology, perhaps more tractable than fundamental physics. A generation ship is a mobile world, a civilization on a multi-millennial journey. Would the culture aboard diverge so much they're a different civilization? Would they even want to complete the mission? This is a fundamentally different enterprise, not individuals traveling in their lifetimes, but launching civilizations on uncertain, multi-generational voyages. If we're serious about biological humans reaching other stars, slow generation ships might be more realistic than fast crewed missions. The dust problem is less severe, energy more manageable, technology closer. The trade-off is time, thousands of years, and all the uncertainties of maintaining a civilization across such scales. Maybe that trade-off is necessary. Maybe the universe tells us interstellar travel is possible only on civilizational timescales. Bringing it together, realistic futures given the dust problem. 1. Robotic exploration only. Most likely near-term. Send sophisticated probes, maybe AI-driven, maybe carrying digital minds or genetic templates. Sidesteps keeping humans alive. 2. Digital migration. Develop mind uploading. Digital minds transmitted or carried by probes. Human-derived intelligence spreads without biological challenges. Are they still human? 3. Slow generation ships. Build large, self-sustaining habitats, traveling at 0.1 to 1% light speed on multimillennial journeys. requires enormous commitment, but might be achievable. Cultures may diverge. 4. Solar system only. Accept interstellar travel as too difficult. Focus on exploring/colonizing our solar system. Study other stars with telescopes. The solar system is vast enough for civilization for millions of years. 5. Breakthrough physics. Discover FTL, wormholes, etc. Science fiction. No evidence it's possible. Unwise to bet on. Futures 1 to 4 are more plausible than the Star Trek future of fast, routine interstellar travel by biological humans. The combined barriers, dust, energy, time dilation, biological needs, social costs, might be insurmountable for traditional crewed missions. We might send robots, information, or slow generation ships. Or we might stay home. What we probably won't do, what might be genuinely impossible, is send large crews of ordinary biological humans on fast ships to other stars and have them arrive alive and intact. The universe is vast and hostile. The very speeds required to cross interstellar distances quickly make the crossing unsurvivable. This contradicts much science fiction and popular expectation, but it's the conclusion from examining the physics, especially the dust impact problem few discuss seriously. We're not prepared for interstellar travel. We lack the technology to protect against relativistic dust bombardment, the energy to accelerate large crewed craft, the closed ecosystems for multi-generational journeys, the social structures for century-scale isolation. These might not be temporary limitations, but fundamental barriers any civilization faces. The speeds required for quick journeys create unsurvivable hazards. The slow speeds that are safe require journey times that create their own insurmountable challenges. We might be trapped not by lack of imagination or tech, but by the universe's structure, the distribution of interstellar matter, the physics of kinetic energy, the needs of carbon-based life, the time scales of crossing light years. If true, the galaxy might be full of civilizations, each confined to their star system, able to observe but never visit, forever isolated by distance, energy, time, and the deadly rain of interstellar dust at relativistic speeds. A lonely cosmos, but possibly the true one. This doesn't mean we stop dreaming, exploring, or pushing boundaries. But we must be realistic about what's achievable, honest about the barriers, and creative about alternative ways to achieve our goals. Whether robotic exploration, digital existence, slow generation ships, or thriving in our solar system. The stars are beautiful, distant, fascinating. We can study them, learn from them. But visiting them, sending humans there to arrive alive, might remain forever in science fiction. We need to come to terms with that possibility, even as we explore every avenue that might prove it wrong. The interstellar dust problem is real, severe, and might be fatal to our dreams of spreading among the stars. That's the truth nobody talks about.